So hello and welcome back. Today is the second part of our lecture on probabilistic motion models. The learning objectives include discussing the difference between a motion model and a sensor model, the difference between two typical motion models, including odometry-based and velocity-based, to discuss how to approximate odometry-based motion model errors, and also to find velocity-based motion model errors, and to discuss how to calculate the posterior probability P of x given x prime and u, and how to sample the probability x given x prime and u, and to discuss our extended motion model that takes into account the map or environment. So now the final topic in this lecture is motion and maps. And this is a problem because so far we have found the value for the probability of the robot's state in a vacuum. We are assuming we know nothing about the world, nothing about the environment, and that the probability of xt is only based upon the control input from the robot as well as its previous state x of t minus 1. We know this is not really true though, because we need to know things about navigable spaces, goals, where the robot can go in the world, etc. So if we have a map M of the robot's navigable spaces, this gives us more information about the robot's pose and where and how it can pose. Note that the probability of xt given ut x of t minus 1 and the map is not the same as the probability of xt given ut and x of t minus 1, which makes sense because now we have more information, so we would obviously make different decisions. So the map-based model in theory should give us better results because you now have the likelihood that a robot can arrive at pose xt if placed in a world with map M and can execute ut at pose xt minus 1 and also can execute from xt minus 1 to xt without hitting things. So computing that closed form is difficult once again, but once again there is an efficient approximation if the robot makes small steps less than half of a diameter. So if the robot makes small steps, then this formula becomes the normalization constant times the probability of xt given ut xt minus 1 times the probability of xt given the map over the probability of xt. So for the map consistent motion model, this is what it would look like for the probability of x given u and x prime. And here's what it would look like for the probability of x given x, u, x prime, and m. And the main thing you should see here is that horizontal rectangle, which is a space that represents an obstacle. So with the map information, we now know that the robot is not able to actually go in that space because there's an obstacle there. But the caveat here is that the star indicates a space that the probability would say is navigable and a pose the robot could get to. However, how could it get there without somehow magically going through that wall? So those are the kind of things you have to consider when you're doing this, is that the probability math may give you some data that is not realistic for the robot. So the algorithms for doing this, the motion model algorithm is motion model with map xt ut xt minus 1m, and you return the probability of xt given ut and xt minus 1 times the probability of xt given m. And then the sample motion model with the map has an input of ut xt minus 1 and m, where you then use the sample motion model first to find xt, which is ut xt minus 1, and then you find a value pi equal to the probability of xt given the map, and if pi is greater than 0, then you return xt pi. And this concludes our final discussion on motion modeling. I hope you've enjoyed it. As I said, as the course continues, it does get a bit more intense, but I know you can do it. I have complete faith in you. Watch the videos more than once. Write out examples, let some of this marinate in your head. You don't always get it on the first try, and come back for more. Have a robotastic day.